All right, welcome everyone. In this explainer, we are going to absolutely master one of the most fundamental properties of signals, periodicity. And to get us started, you just need to think about the phone that's probably in your pocket right now.
Think about it. Your phone's ringtone. It plays that same melody over and over again, right? That's a classic periodic signal. But that one-time notification beep, that's aperiodic. Now, this seems like a simple difference, but it has huge consequences in signal processing. For instance, those repeating periodic signals have infinite energy, while the one-off aperiodic signals have finite energy. Getting this distinction right from the get-go is absolutely crucial.
So why are we drilling down on this right now? Well, because figuring out if a signal is periodic is the very first step you have to take before you can unlock one of the most powerful tools in engineering, the Fourier series. You're going to be diving deep into that in week 4. And I promise you, getting this concept locked down now is going to make your life so much easier then.
So here's our game plan. This lines up perfectly with subtopic 2.3 in your course book. We'll start with the basics of continuous time signals, then we'll navigate that common trap that's waiting for you with discrete time signals. After that, we'll see what happens when we start adding periodic signals together, and we'll wrap it all up with a checklist to make sure you've got it.
Okay, let's kick things off with continuous time signals, or CT signals. You can think of this as our baseline. It's the most straightforward and honestly the most intuitive case when we talk about periodicity.
So here's the formal definition, the mathematical test. A signal, x of t, is periodic if we can shift it in time by some amount, we'll call it t0, and the signal looks exactly the same. But here's the key. The smallest positive value of t0 that actually works is what we call the fundamental period.
And lucky for us, for the signals we see all the time, sinusoids, there's a really simple and elegant formula. The fundamental period, t0, is just 2 pi divided by the angular frequency, omega naught. And remember that omega naught is just the number that's multiplying t right inside the cosine or sine function.
Okay, time for a quick practice run. Take a look at this signal. X of t equals cosine of 8 pi t. Based on the formula we just saw, what do you think its fundamental period is? I'll give you a second to work it out.
All right, let's walk through it together. First step, we identify our angular frequency, omega naught. In this case, it's 8 pi. Easy enough. Next, we just plug that into our formula. T0 equals 2 pi divided by 8 pi. The pi's cancel out, which leaves us with 2 over 8. And that simplifies down to 1 over 4. So the fundamental period is 1/4 of a second. See? Pretty straightforward.
Okay, now that we're comfortable with continuous time, let's switch gears to discrete time signals. But I have to give you a warning. We're about to encounter what's often called the discrete time trap. There's a really crucial difference here that trips up a lot of students, so you want to pay close attention.
And here it is. This is the heart of the trap. For continuous time sinusoids, they are always periodic, no ifs, ands, or buts. But for discrete time sinusoids, that guarantee is gone. They are only sometimes periodic. And what that means is you have to test them every single time to be sure.
So here's the critical test you have to perform. A discrete time sinusoid is periodic if and only if its digital frequency, we call that capital omega naught, divided by 2 pi gives you a rational number. And remember, a rational number is just a fraction of 2 integers, like 1 over 8 or 3 over 2. If that ratio is an irrational number, like pi or the square root of 2, then the signal is aperiodic. The samples will never, ever perfectly repeat.
All right, your turn to try this out. Is the signal x of n equals cosine of pi n over 4 periodic? And if it is, what's its fundamental period, and not? Remember the 2-step process. First, check for periodicity, then find the period. Go for it.
Let's break this down. First, our omega naught is clearly pi over 4. Now for the crucial test. We take that and divide it by 2 pi. So pi over 4 divided by 2 pi gives us 1 over 8. And since 1 over 8 is a rational number, yes, the signal is definitely periodic. Now to find the period, and not, we can actually see it right there in that rational number, 1 over 8. The fundamental period is 8. This means that this sequence of samples will perfectly repeat itself every 8 samples.
Okay, so we've got a handle on single signals. But what happens when we take 2 periodic signals and add them together? Is the new combined signal still periodic? Let's find out.
This table lays it all out really clearly. For continuous time signals, the sum is only periodic if the ratio of their individual periods, t1 over t2, is a rational number. But check this out for discrete time. Here's another one of those little surprises. The sum of 2 periodic dt signals is always periodic. No extra test needed. And in either case, if you want to find the new fundamental period of the sum, you just use the least common multiple, or LCM, of the individual periods. Okay, one last example to tie this all together. Let's look at the signal x of t, which is the sum of cosine 2 pi t and cosine 3 pi t. Is the signal periodic? Now remember the steps. You've got to find the individual periods first, and then test their ratio.
Let's do this step by step. The first signal, cos of 2 pi t, has a period t1 of 1 second. The second signal, cos of 3 pi t, has a period t2 of 2/3 seconds. Now, for the test, we take the ratio of t1 over t2, so that's 1 divided by 2/3, which gives us 3/2. Hey, that's a rational number, so the sum is periodic. To find the overall period, we take the LCM of 1 and 2/3, which works out to be 2 seconds. And this makes total sense if you think about it. After 2 seconds, the first signal has completed 2 full cycles, the second has completed 3 full cycles, and that's the exact moment their combined pattern starts to repeat.
We've covered a lot of really crucial ground here, so before we finish up, let's just run through a quick checklist to consolidate everything we've learned and to make sure you're feeling confident applying these skills.
Okay, take a second and look at these 4 key skills. Can you confidently apply the continuous time test and find T0? Can you handle that critical discrete time rationality test and avoid the trap? Can you find N0 for a discrete signal? And finally, can you determine the period of a sum using the LCM? If you can put a mental check mark next to all 4 of those, you are in fantastic shape.
And that brings us to the final and really the most important question. These tests, they aren't just some random academic exercise. They are the essential foundation for what's coming next. By truly mastering them, you're getting yourself ready for the incredibly powerful analysis you'll be doing with the Fourier series. So, are you ready? Thanks for joining me for this explainer.